Hello class. Today I wanted to look at a problem from chapter 6, motion in 2 dimensions. And what I'm going to do is I'm going to read the problem to you. We're going to talk about some given information, and I've drawn a diagram, and I'm going to go through this step by step to help you solve the problem. So let's go ahead and get started. A pitched ball is hit by a batter at a 45-degree angle and just clears the outfield fence that is 98 meters away. If the fence is at the same height as the pitch, calculate the velocity of the ball when it left the bat. So I have some information documented here. The angle is 45 degrees with respect to the horizontal or the x-axis. Our displacement in the x direction is 98 meters, and on the diagram I have that here. Range is equal to 98 meters. Now here's our initial velocity vector, and we know that we can use vector resolution to break that into the x and the y component of the initial velocity. But before we do that, I want to point out a few things. The first thing is right here where the bat comes in contact with the ball, we have a time equal to 0 seconds. Okay? So the time just begins when the bat comes in contact with the ball. And in the y direction, y is equal to 0 meters. Okay? Now, when we hit the ball at 45 degrees and it comes back down and it just clears the fence, the problem tells us that we are at the same height. So right here, our final vertical position is also 0 meters. And right here, we can call this our final time or our change in time, but we don't know what that is right now, okay? So let's talk about vector resolution. Okay, we know that the velocity in the x direction is equal to the initial velocity times cosine of the angle theta, okay? Well, we know the angle theta is 45 degrees, so we have initial velocity times cosine of 45 degrees. And then for our y component of velocity, we have velocity in the y direction is equal to initial velocity times sine of the angle theta. Well, our angle is 45, so d sub I times sine of 45 degrees, okay? So what we have here is velocity in the x direction is equal to, let's see what cosine of 45 is, square root of 2 over 2. So we have cosine 45. Let's get the decimal value. I have 0.707. And so we can say 0.707 times our initial velocity. And I just want to put the numerical value in front of our variable here. The velocity in the y direction is going to be 0.707 v sub I. Okay? All right, next we can use the equation. The final position in the y direction is equal to the initial position in the y direction plus v sub I sub y times delta t plus 1/2 g delta t squared. Okay? Now let's take a look at the final position in the y direction. Let's take a look at our diagram here. So earlier we identified that the final position in the y direction is 0 meters. This is equal to the initial position in the y direction. So earlier we talked about the initial position over here. It's just where the bat and ball come in contact with each other, so that's 0 meters. Plus, so my initial velocity in the y direction is right here, 0.707 times v sub I. Times delta t plus 1/2 times the acceleration due to gravity, so that's negative 9.8 meters per second squared, multiplied by delta t squared. Okay? Now what we can do is we can clean this up a little bit. Just to make this really clear, I'm going to leave the 0 meters on the left side of the equal sign. Right here, we're going to get rid of this 0. And what we're going to do is we're going to factor a delta t out of this. So what I have, I'm going to say 0 meters. I'm going to use my hard brackets so I know that I'm factoring a variable out here. 0.707 times v sub I. Okay, we're factoring delta t out, plus, now what we have here, negative 9.8 meters per second squared times 1/2, or divided by 2 is negative 4.9 meters per second squared. We're multiplying this by delta t, just 1, because remember we're factoring a delta t out of this, okay? Now remember that this is a quadratic, so we can have two different answers here. And so if I split this up, we have this right here, what we factored out. Delta t is equal to 0. And this is one of our times. Well, let's take a look at this. Delta t equal to 0. Well, we know our initial time is 0 seconds, okay? So that looks good. Now this part is going to be equal to 0. So what we have is 0.707 times v sub I plus, or we can say minus, 4.9 meters per second squared times delta t is equal to 0, okay? Now what we want to do at this point is isolate delta t. So we need to solve for delta t. The first thing we're going to do here is we are going to subtract 0.707 times v sub I from both sides of the equal sign. And then we are going to divide by negative 4.9 meters per second squared. So this is going to give us delta t is equal to a negative 0.707 v sub I divided by negative 4.9 meters per second squared. Okay, let's grab our calculator here so we can clean this up. So I'm going to do my division here, so we know we're going to get a positive sign, and we can multiply that by v sub I. So delta t is equal to 0.144, and let's take a look at our units here. So I have meters per second squared in my denominator, and we're going to flip that. For the inverse, we have second squared over meters times our v sub I, okay? So we're going to need to keep this here. Now we need to talk about range. So we know that range is equal to the velocity in the x direction multiplied by delta t. Now we know that our range is 98 meters. So they tell us this in the problem. So we have 98 meters is equal to velocity in the x direction. I have 0.707 times v sub I multiplied by delta t. Okay, what I want to do at this point is isolate delta t, okay? So delta t is equal to 98 meters divided by this here, 0.707 times v sub I. So what I'm going to do is my division, and we're going to have initial velocity in our denominator. So 98 divided by 0.707 is equal to 138.61. divided by V sub I. And let's not forget that we have units of meters here. So that's what delta T is equal to. So what we need to do right now is we need to plug in this for delta T right over here, okay? So delta T is equal to 0.144 seconds squared per meter times the initial velocity of our object. So we have 0.144 seconds squared per meter multiplied by initial velocity is equal to 138.61 meters divided by initial velocity. Okay? So what I want to do is multiply both sides of the equal sign by initial velocity. And so on the right hand side we have initial velocity in the denominator. So to get rid of it, we're going to multiply both sides here by initial velocity. And so on the right hand side, that cancels out. Now we know on the left hand side, initial velocity times initial velocity is going to give us initial velocity squared. So what we have here is 0.144 seconds squared per meter times initial velocity squared is equal to 138.61 meters, okay? Now what we want to do is divide both sides by the 0.144 seconds squared per meter because we're trying to isolate initial velocity squared, okay? So initial velocity squared is equal to 138.61 meters divided by 0.144 seconds squared per meter. So let's talk about the numerical value first here. So 138.61 divided by 0.144, this gives me 962.59. Okay, now let's talk about our unit value. We have meters divided by seconds squared over meters, and we can write this as meters over 1 divided by seconds squared over meters. And remember the old algebra rule that tells us whenever we divide fractions, it's like multiplying by the inverse of the denominator. So what we have here is meters over 1 times meters over seconds squared. So this is going to give us meters squared per second squared. Okay? On the left-hand side of the equal sign, we have initial velocity squared. To eliminate our squared, we need to take the square root. And remember, what you do to one side, you have to do to the other. So we're going to take the square root of this value. And that gives me 31. Okay? Now right here, we're taking the square root of the unit value as well. So the square root of meters squared per second squared is meters per second. So our initial velocity right here, initial velocity is equal to 31 meters per second. And remember, this is a vector, so we need to include direction. Well, we know that the ball left the bat at an angle of 45 degrees. So we need to say initial velocity is equal to 31 meters per second at 45 degrees. And that is the answer right there. Okay? I hope this video helps you out with this problem. If you need any help, just give me a call or you can send me a message. I hope you have a wonderful day.